So now in this video, we're going to talk about intermolecular forces. Now, intermolecular forces are forces that act between molecules or discrete atoms and holds them close to one another. And so just to kind of give a visual understanding of what that simply means. So let's just say if we're talking about, for example, I'm going to draw this to the side. If we're talking about a water molecule, so here's a water molecule, here's oxygen, here's its two hydrogens, and then we're looking at another water molecule, oxygen is two hydrogens. The intermolecular force are just forces of attraction between these two molecules or between many molecules, all right? So if you think about like intermolecular forces, much like the prefix inter, meaning amongst others, like international, like relations between different nations, or if we're talking about like an interstate, where we're looking at a road or interstate road like I-75 or I-285, you know, I-285 is not a good example. Like I-85, where it's a road that connects different states together. Intermolecular force, it's a force between different molecules, all right? And so in this class, we're really going to focus on these three, which are London dispersion forces, dipole-dipole forces, and hydrogen bonding forces. And we're going to talk about what they are and what affects them, and then what can you do and what clues that you could look for to identify what type of intermolecular force a group of molecules may have for one another. All right, so the first one we're going to talk about is London dispersion force. Okay, so now London dispersion force, it's basically, well, let's kind of talk about what type of molecules that exhibit London dispersion forces. All molecules exhibit London dispersion forces, okay? And so just to kind of put this out there, you know, you may have many different molecules that may have or exert multiple different types of intermolecular forces all at the same time. Now, there's difference in relative strengths of each of these forces, but you'll find that many of them will have many of the same or many different type of intermolecular forces all at the same time. All right, and so all molecules experience these type of forces, and when it comes to London dispersion force, all molecules experience it. All right, but this is the only force that are within nonpolar molecules. All right, and so it's really important. With intermolecular force, you will have to actually determine if the molecule is polar or nonpolar. All right, able to determine if a molecule is polar or nonpolar will help you able to figure out what type of intermolecular forces these molecules are exerting. Okay, and so for nonpolar substances, as I said earlier, London dispersion force is the only force that they exert. Okay, polar substances, this is not the only one. They also exert London dispersion forces, but they also have stronger forces. Now, of all the intermolecular forces that we're going to talk about, London dispersion force is actually the weakest of them all. Okay, so between dipole-dipole hydrogen bond and London dispersion force is the weakest one. Okay, now what is London dispersion force? It's like what causes it? All right, so I'm going to kind of just blow up into this thing here. All right, this illustration here we see is if we're talking about a nonpolar substance. Okay, so here's a nonpolar substance. Let's just say this is these two substances are H2. Okay, these are nonpolar. All right, and so that means electrons are being shared equally between the two. All right, so I'm going to draw some electrons. So they're sharing electrons, okay, between the two. Now, electrons are not static. They don't stand still, you know, especially shared electrons in any type of molecule. All right, so it's not like the electrons are just standing still between the two different nuclei and stuff like that. I know sometimes we draw lines, and I guess in our minds, we're thinking, oh yeah, the electrons are standing still between these two nuclei. No, they're not. They're actually moving around. Okay, they're moving around left and right, up and down, stuff like that. And so because the electrons can move around, all right, so in an instant, all right, in a particular instant, let's just say, and I'm going to move on to the second picture here. Let's just say the electrons were here, all right. The shared electrons is closer to the nucleus on the left. Because, as I said, electrons just move around, so it's completely random. All right, so if that's the case, what happens is that then this molecule gains a temporary polarity. All right, remember, it's very temporary. It's not permanent because, as I said, the electrons are being shared equally between both of these nuclei. So the electrons will then leave it at some point, but it gains a temporary charge. So since the electron is closer to the nucleus on the left, then the nucleus on the left will have a partial negative charge, while the nucleus on the right will have a partial positive charge. Okay? And just only for that moment until the electrons move. Okay? Now, let's just say for the second atom here, of course, let's say the electrons remain in the middle, but let's just say the electrons are moving around, and it sort of happened that around the same time when the electrons were on the left side of this atom, that these electrons will also move to the left side of the atom, right? And what's going to cause, just like the first H2 molecule, where one side was partially negative, that looks like a 5, negative, and the other side is partially positive, this happens here as well. You have a partial negative and partial positive. What does that cause? Well, then, if you notice, as these molecules are adjacent to one another, the opposite charges are next to each other. Now, because the opposite charges are next to each other, there is this attractive force between these two molecules, all right? And it's a very temporary attractive force because, let's just say we were to go back up this way, and this set of electrons move back towards the other side, well, then it will lose the partial charge, and then the attractive force will disappear, all right? It will no longer be there. So this attractive force, this intermolecular force, or IMF we call it, is what we call the London Dispersion Force, or LDF, all right? And so, in short, we basically have, because electrons are moving back and forth, it will create these temporary partial charges or temporary polarization of the molecule, where we will now see polar parts of the molecule, where you have a part that's slightly negative and a part is slightly positive. And if we have that going on at the same time between different particles, all right, then the opposite charges, the opposite charge side are facing each other, then there's going to be this attraction. Now, this attraction, as I said, we call this attraction London Dispersion Force, all right? And so that's the big thing. It's a very temporary thing, all right? It comes and it goes. Now, when it comes to the strength of the London Dispersion Forces, the larger the molecular weight of the molecule, all right, the larger the molecular weight of the molecule, and the larger the surface area of the molecule, the greater this temporary polarization of the molecule, all right? So the greater the London Dispersion Force. So what does that mean? So, like, quick example, if you had CH4, so CH4 is a nonpolar molecule, all right? So that means if you have a pure sample of nothing but CH4s, okay, the CH4, from one CH4 to another, the type of intermolecular force that we'll have is London Dispersion Force, all right? Versus if you had something like C6H14, okay, this is also a nonpolar molecule, all right? But if you notice, compared to C6H14 and CH4, C6H14 is a much bigger molecule, all right? And so because it's a bigger molecule, it also will exert London Dispersion Forces with all other C6H14s, if you're talking about pure sample. But this London Dispersion Force, the forces within C6H14 will be much stronger than CH4 because C6H14 is a larger molecule. All right, it has a greater molecular weight, and it also has a larger surface area. All right, so next we're going to talk about dipole-dipole forces. So now dipole-dipole forces consist of polar molecules, all right? And it's where the positive and negative ends of the different molecules are attracted to one another. All right, so let's look at this example here. So HCl, okay, so we have HCl here. So these two molecules are both polar molecules, all right? Now, what's one of the main characteristics of polar molecules is that they have a permanent polarities between opposite sides of the molecule. So that means that one side is slightly negative, the one and another side is slightly positive, and it's permanent. And that's just due to the difference of electronegativities throughout the compound itself, or in a sense, it's the unequal distribution of electrons around the molecule. And so we see here that hydrogen it has a permanent partial positive charge. Chlorine has a permanent partial negative charge. And this is true for the other molecules here. And so due to the fact that you have these opposite sides that are attracted to, or who have opposite sides with opposite charges, or different molecules where each side has a opposite charge, right? There's going to be attraction for one another. There's this attraction here. This attraction is the intermolecular force, and this intermolecular force is specifically dipole-dipole. So hydrogen bonding, the last of the intermolecular forces that we're going to talk about, it's really an unusually strong dipole-dipole interaction. So this is the reason why we kind of categorize it as its own. But basically, it's an attraction between a hydrogen atom that is bonded to an oxygen, nitrogen, or fluorine, and is attracted to a nearby oxygen, nitrogen, or fluorine. Okay? And so let me show you an example. So a good example of this is water molecules and their attractions for one another. And so if you look, according to the diagram here, we see that here we have water molecule, right? So we have one dead in the center. All right, this hydrogen has a partial positive charge, and it's a permanent one. The oxygens have a partial negative charge. All right, this hydrogen is attracted to the oxygen over here, which makes that this bond that we see here, or well, at least all these bonds that we see here, all right, these IMF is specifically hydrogen bonding, because you have a hydrogen, all right, that is bonded to an oxygen, okay, that is attracted to an oxygen, okay. And so remember, hydrogen bonding is an attraction to either a fluorine, oxygen, or nitrogen. And this particular hydrogen has to be bonded to fluorine, oxygen, or nitrogen. Fine, okay? And so that's hydrogen bonding. Now, as I said, hydrogen bonding is actually of the strongest, right? And so if you were to rank them, right, in terms of strength, London dispersion force is the weakest. And then you have dipole-dipole force. And then stronger than dipole-dipole is your hydrogen bonding. All right. Now, we could see this in different ways. All right. So like melting points, boiling points, we could see a factor that affects melting boiling points of different substances is due to the intermolecular forces. All right. And so this is actually the reason why nonpolar substances tends to have the lowest boiling points / melting points, because the intermolecular force of the London dispersion intermolecular force is a relatively weak one, so it doesn't take much energy to break those, versus those that consist of hydrogen bonding. These polar molecules, they tend to have higher boiling point slash melting points. All right. And this is why water particularly has a high melting point, high boiling point compared to other molecules roughly the same size as the water molecules. All right. And so this is intermolecular forces.